All right, so today we're going to get into Chapter 3. And Chapter 3 is all about numeric summaries for numeric data. We'll also start using the clickers today. So I downloaded the roster that CCLE had of people who had clickers registered to their accounts, and it had a lot of you. A lot of you guys were registered, but a lot of you were also missing from the list. So today I'll try to just keep it to easy questions, and then you can just and I'll upload the scores. Normally I'll just upload the scores once a week at the end, and then and you can do it, and you can check to make sure you're getting your points. But today I'll upload the scores later today, and you can check to make sure you're getting credit for your remote. So if you have a remote but CCLE shows that you didn't get any points, then there's an issue with your clicker registration with CCLE. You know, if you get your points, then that's great. And if you don't have a remote yet, please try to obtain a remote as soon as possible. Okay, so we're talking numeric summaries for numeric data. And the big idea here is that, you know, in your sample of data, you might have hundreds of observations, even thousands, or possibly even millions of observations. Okay, so the big idea is that your data set may have thousands of observations. And all of that information is just too much for our brains to handle. And so we want to find a way to just kind of boil that in all of that data into just a few numbers that we can take a look at. So if we want to compare one data set and another data set, you know, we don't want to have to deal with thousands of observations. For example, if we want to compare the student body of UCLA students versus the student body of, I don't know, let's say NYU, okay? You know, there's thousands of students at each of these schools. And if we just gave you the raw information and just said, okay, here's one student and here's all of the student's information. Here's another student, here's all of the information for the student. And we just gave you, you know, a spreadsheet with, you know, 40,000 rows on it for UCLA, and then we go to NYU and get, you know, I don't know, however many thousand rows over there. We're not going to be able to do much in the way of comparison, okay? However, if we can just kind of create numeric summaries, so we create the average, I don't know, the average GPA of students at UCLA versus the average GPA at NYU, then now we just have one number over here and one number over here that we can compare, and that makes our lives a lot easier. And so that's the whole idea behind numeric summaries. We want to find ways to boil down lots of information just down to just one or two numbers, or maybe even more than that, but just a few numbers that we have for this data set and a few numbers that we have for that data set. Okay, so we may have thousands of observations. We probably don't want all of the details. So numeric summaries try to boil down Okay, so we try to boil it down just to a few values, and then now that we have just a few values, we can make comparisons between groups a lot easier. Okay. Okay, and so you guys are familiar with lots of numeric summaries, and today we're going to cover topics like the mean and the median and this variance and things like that. But numeric summaries don't have to just be these things like the mean and the median. You have something like the GPA. The GPA is an example of a numeric summary, and the GPA is supposed to be a single number that summarizes your entire academic career or academic performance, right? It's, how did you do in college overall? We try to summarize that with a single number, so much so that you might put this on your resume if you're proud of it, okay? But if the problem with the numeric summary is that its strength is also its weakness, in that it takes a lot of information and it boils it down to a single number, but because you're boiling it down to a single number, it loses a lot of detail, right? So some of you might have had one quarter where just a lot of personal issues were going on and it hurt your academic performance, and the GPA is not going to say this number, it just averages everything together, so it doesn't tell the story behind everything, right? And so that's the other, that's the double-edged sword of a numeric summary. If you're into sports, then whatever sporting thing you can think of, people have created numeric summaries for this, right? So if you're into football, American football, the quarterback gets a passer rating, and it's just a single number that's supposed to indicate the overall performance of the player. If you are into basketball, you might have shooting percentages or different things. It's just a single number that's supposed to summarize the performance of an athlete. Okay, and of course it doesn't tell the whole picture, but it's useful to just kind of make quick comparisons. As far as economics around the world, we can just kind of compare the relative economic strength of one nation to another nation with a single number, right? We just say, oh, the GDP of the United States is this huge number versus the GDP of some other country is this, or we can say, look how much China has progressed because the GDP of China 50 years ago was this, and today it's this, and we can say that's an indication of how much economic growth China has undergone. And it's just a single number that's supposed to kind of capture the big picture idea, not tell the whole detail of everything, right? So okay, so let me just kind of list off a few examples. So the GPA, it's single value. And then so these are kind of numeric summaries that serve specific purposes. We have kind of just generic numeric summaries. Generic numeric summaries that work for any numeric set of data. Okay, so we have summaries for the mean and median. I'm sorry, not summaries for the mean and median. Summaries for the center, which are the mean and median. Summaries for the center, I apologize. Okay, and then summaries for the spread. Which will be the IQR and the standard deviation. I should write that the other way around. Standard deviation and IQR. Okay, I'm hoping all the students are here and no one's coming later than this. But so we'll just run a clicker question here. There's no, it's not actually going to be a question. It's just going to be click your remote, and this is mostly to be a test to see if your remote is working. Okay. So if you turn your remote on, it should I don't know, it should show stats 10 in this welcome screen if you have a screen. If you don't have a screen, then that's okay. We'll just say go ahead and click answer choice A. Okay, so everybody go ahead and click A, and okay, so I've got 127, 130. Some of you are not clicking A, but we'll just go ahead, if you've got a remote, go ahead and click A, and this thing is going to just pick up everybody's remote. And so whether it's registered with CCLE or not, your remote will register a click here. It's just when I upload the scores, it will upload your points to your student account or your student ID based on what's registered to it. Okay, so if you haven't registered your remote, it will just show up in my system as remote code A B C D E F G, but unregistered or something like that. Otherwise, it will show. Okay, is this everybody? 137 of you? Okay, well, I'll go ahead and click stop, or 138. Okay, so I'll go ahead and click stop, and then later today I'll upload the scores from these remotes, and you should get points. Okay, if you have a remote and you clicked, then later today when you check CCLE, it should show that you've received a point for today's session, and it'll be 2 points. Okay, one for attendance, and then one for getting the question correct. So every question is worth a point, and then you get a participation point. So if I ask 3 questions during a lecture, there will be 4 points total, up to 4 points total. You'll get 1 point for participating, and then each question you get correct, you'll get another point. Okay, so if you get them all wrong, you'll get 1 out of 4, and if you get them all correct, you'll get 4 out of 4. All right, so we'll go ahead and try that. Okay, let's indicate that was the correct answer. Okay, so regarding our numeric summaries, we have some guidelines or suggestions for usage. Okay, and these are just suggestions because all of these numeric summaries can be used for all sets of numeric data. Okay, so these are just guidelines because can be okay, and so the guidelines are if your data is skewed. So what does it mean to be skewed? It means you've got kind of a pointy tail, something like this. So this one is right skewed, and this one is left skewed. So if your data is skewed, the suggestion is to use the median for the center. Use the median and the IQR for the spread. And on the other hand, if your data is symmetric, the suggestion use the mean and the standard deviation. Okay, and again, any of these numeric summaries can be used for any numeric data set. These are just suggestions, okay? And part of the reason why we have these suggestions is that the median and IQR so here's kind of our reasoning, is that the median and IQR are not affected by extreme values. So when you have data that is right skewed, okay, that you would have extreme values on the right. If you have data that's left skewed, you have extreme values on the left. When you have symmetric data, the extreme values on the right balance out the extreme values on the left. So that's okay. But you know, if you have extreme values only on one side, that could affect your thing. And so the median and IQR are not affected by extreme values, whereas the mean and standard deviation are affected. I'm going to just abbreviate standard deviation as SD, are affected by extreme values. So in symmetric data sets, the extremes balance each other out. Okay, so here we go. Those are just suggestions. Again, it doesn't have to be that way. All right, so let me give you a data set, or just an example of how this kind of works. Okay, so imagine we have some family. Okay, so we've got, just imagine the, I don't know, Thompson family. Just making this up here. Okay. And they have 4 kids. And I'm going to just write the numbers starting over here. Let's say the kids' ages, we'll say the oldest is 16, the next is 15, the next is 14, and the youngest kid is 2. Okay? So you can, I don't know, we could make up a backstory for the Thompson family, but let's say this is what the children's ages are. And so we'll make a dot plot. Okay? So starting at 0, I'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, and then I'm just going to put dots along, create a dot plot. So we got a dot at 16, a dot at 15, a dot at 14, and a dot at 2. So this is my dot plot here. Okay, if we calculate the mean is, I think we're familiar with this. We add up all of the x values and we divide by how many we have. So I go 2 plus. Are you guys okay with this symbol? This symbol just means add them up. It means sum, which just means add them up. Okay. So the Greek letter sigma. It's the Greek letter for S. S as in sum. And then so this sum just means to add up. Okay, so we add all of these up. We get 47 divided by 4. I get a mean of 11.75. And so what 11.75 is, this is the mean. And we can think of the conceptual definition, okay? Conceptual definition of the mean. Okay, and that is the balance point of our data. And so you can imagine putting like this being a plank, a seesaw, and these are incredibly heavy stones. If I want this thing to be balanced, then I would put the fulcrum right here at 11.75. Okay, so the fulcrum, the balance goes here. And then our seesaw would be balanced. Okay. So this is our balance point. Okay. And so, you know, if somebody said, you know, what's the average age of kids in the Thompson family, it is technically correct to say that the average age of the kids is 11.75, just under 12 years old. But would you say that really tells the whole story of what's going on at the Thompson household? Not really, right? Most of the kids are, you know, 14, 15, 16. They're right around 15 years old. They're in high school doing, I don't know. And then, but then they also have a 2-year-old. And so saying that the average age is just under 12 years old, while technically correct, doesn't really tell the whole story. Okay, so in this case, you know, for skewed data, the mean let's say 11.75 does not really tell the whole story. Okay, let's just do a quick comparison between. So that's the Thompson family. Let's just say we've got the Smith family, and let's say the ages of the kids in the Smith family, also 4 kids, and let's say the ages are pretty much the same except the last one, you know, let's say that goes 13, 14, 15, and 16. Okay, so the first 3 kids the same, 16, 15, 14, and then the last kid is 13. And so in this case, our mean is, we add these up, we divide by 4, and I get 14 and a half. If we create our number line, we just start at 10. And, it makes sense that the balance point is right here. Yeah, 14 and a half. So comparing the Smith family to the Thompson family, we can see that, in the Thompson family, the extreme value that was the very young child, that pulled the value of the mean in the direction of the skew. Okay, so here this is our data is symmetric. So with symmetric data, okay, the mean adequately describes the center of the data. Whereas in skewed data, mean gets quote unquote pulled in the direction of the skew, so that, on the previous slide, the kid aged 2 brought the mean value down. Okay, that's what we have there. So today we're going to just talk about numeric summaries for symmetric data. So we'll talk about the mean, and then we'll talk about the standard deviation, and then on Wednesday we'll talk about the median and the IQR. Okay, so that is the mean to describe the center. And then the other part that we need to talk about is describing the spread of the data. Okay, so another aspect to summarize is describing the spread of a sample of data. All right, and so think of the ages of people in just think of the ages of people. Okay. Okay. Let's say we go and we visit a 2nd grade classroom. In a 2nd grade classroom, if we think about the age of the children in the 2nd grade classroom, about how old are these kids? They're around 7 years old, right? So if we think about them, almost all of the kids will be about 7, okay? maybe you might have a few 6-year-olds and maybe a few 8-year-olds, but by and large, most of the kids will be 7. Okay, so maybe a few who are 6 and a few who are 8, but most of them will be 7. Okay, and so if we talk about the spread of ages in the classroom, the spread of ages will be very small. All right, let's imagine another classroom. Let's just say this classroom. Okay. All right, what is what are kind of the spread of ages that we have in this classroom? Okay, probably most, I don't know, are between 18 and 23, but then we're going to have some who are older. Okay, and you know, the upper age limit could, there's no real limit, but you know, probably 80% or more of you are between 18 and 23, and the remaining, you know, 10 to 20% different ages. Okay, so in this case, we're going to have you know, more spread than the second grade classroom. Okay, all right, and then imagine going to the DMV, and we'll go to the DMV waiting room. Okay. So what kind of ages will we see in the DMV waiting room? DMV is the Department of Motor Vehicles. This is where you go to get your driver's license and register your cars and things like that. So here we're going to see lots of different ages, right? We have teenagers getting their licenses, okay? Teens getting their license. We'll also have, you know, I don't know, middle-aged people registering vehicles and taking care of stuff like that. We'll have seniors, okay? And then, you know, some of these, quote, middle-aged people, they might have their kids, and or, you know, we might have young parents bringing their children along, so there could also be children. You've got, at the DMV waiting room, you have a very high amount of spread as far as ages go, okay? Okay, and so the concept with spread is that with low spread is that the values in the data are not spread out on the number line, but rather they are quite similar to each other. Okay, low spread. So you can think about, you know, the values are not very spread out on the number line. Rather, the values are similar to each other. Okay, and high spread is just the opposite. The values are very different from each other. Meaning that they are very spread out along the number line. Okay, and so the standard deviation and the IQR, in particular, the standard deviation that we're talking about today, this is a value that gives a number for spread. So rather than saying this has high spread and this has low spread, which are kind of vague terms, we can say the standard deviation of this set is 2. The standard deviation of this set is 15.5. And we can say, okay, well, this set has a standard deviation of 15.5. Its spread is a lot more than this data set where the standard deviation is 2. So rather than just saying high spread and low spread, we're giving it numbers, which gives us a better picture of the exact amount of spread that exists. So let's do this. Okay, so this is the idea behind the standard deviation. Okay. So I'll give you kind of like the formula and the steps for calculating the standard deviation, but the important part isn't. I mean, it is important that you know how to calculate it and find it, but I think the most important part is that you are able to tell the people what a standard deviation is. Okay, so a standard deviation is just a way, it's a value that quantifies the amount of spread. Okay, so rather than saying high spread or low spread, we can say the standard deviation is this. And of course, depending on the context that we're talking about, 16.4 may be a big number or a small number, right? Because you could have other sets of data where the standard deviation is, 1,000, okay? And it all depends on the context that we're talking about. Okay, and so, how can we define the standard deviation? Okay, so there's another concept very closely related to the standard deviation, and that is the variance. And I'm gonna just say this. I'm gonna say the standard deviation is equal to the square root of the variance. Okay. Don't get squares and square roots mixed up. Okay. Square root of 9 is 3. The square of 9 is 81. And so the square root of the variance and the variance, we can define this as the quote average squared distance from the mean. Okay. So the symbol for the standard deviation is S, and the variance is then S squared. Okay, so I'll throw another. I think this is an easy clicker question, so we'll do this. Okay, so we've got two families. We have two families, and in both families, the ages are symmetric, and the average age is 9. Okay, so two families, both families have average age 9, and we'll say 5 children, and symmetric. So you feel like, oh, we're describing quite a lot, right? The shape of the data is symmetric. There's 5 kids. The average age is 9. What we're missing is the amount of spread, all right? And so let's say we've got the Baker family, okay? So the Baker family, the kids' ages are 1, 5, 9, 13, and 17. And for, we'll say, the Johnson family, the kids' ages are 7, 8, 9, 10, and 11, okay? Both 5 kids, both average age of 9, both are symmetric. But when it comes to the spread, these are your answer choices. You can choose A on your clicker if you think the standard deviation of the Baker family is that greater than the standard deviation of the Johnson family, or is the standard deviation of the Baker family is that less than the standard deviation of the Johnson family, or do you think they are equal? So standard deviation of the Baker family versus standard deviation of the Johnson family. Okay, so your choices are A, B, and C. I think this is pretty easy. So the question is, which family has more spread in the ages? Do the kids in the Baker family have more spread, or do the kids in the Johnson family have more spread in ages? Huh? You can't answer yet? Is it still closed? It should be open. It should. I'm registering clicks here. I got a bunch of people who clicked certain things. Well, you know what? You guys can talk to your neighbors if you're not sure about what you think your answer should be. You know what? Let's just keep everything easy today. I'll tell you, it looks like most of you guys have it correct. Maybe like 3 of you clicked the wrong thing. So the answer is A. So go ahead and just click A. Some of you are clicking D. I don't know why. What's going on here? So click A. All right. This is what we got. Okay. So I don't know, Mr. and Miss D here, and E. Now you guys are just trolling me here. All right. Well, I'm gonna close the poll here. So if you are the not choice A, you're gonna miss out on your points. But I'm gonna go ahead and close the poll. All right. And so everybody except these two should have 3 out of 3 points for today when they check on CCLE. Okay, let me we'll just run through the quick calculation here. So I've defined the variance as the average squared distance from the mean. So let's go through this. Okay, so we're going to say the variance is equal to the quote average, and the average is in quotes here, average squared distance from the mean. Okay, and so I'm going to go ahead and list off the kids' ages in the Baker family. And those ages were 1, 5, 9, 13, and 17. Okay, and so kind of your first step will be, step 1 will be find the mean. And we've already done this, and we found the mean to be 9. Okay. And then so our next step will be to find the distances from the mean. Okay, so how do we get the distance from the mean? Well, I'm going to say how far is the value 1 from 9? And it is 8 away. How far is the value 5 from 9? It's 4 away. How far is 9 from 9? It's right there. 13 from 9 is 4. 17 from 9, it's 8 away. Now, I guess I could put the negative signs here. It doesn't really matter, because the next step is once we get the distances from the mean. Is this okay, everybody? We have our distances from the mean. We want the squared distance from the mean. So we're going to take each of these values and we square them. So we do a -8 squared. Anytime you square a negative number, you get a positive number. So we get 64, we get 16, 0 squared is 0, 4 squared is 16, 8 squared is 64. So these are our squared distances from mean. So far so good? Okay. And now we want to get the average. And I put average in quotes because normally to get the average or the mean is you would add them up and divide by n. What we're going to do here is we're going to add up and divide by n minus 1. And that will give us the variance. So I do 64 plus 16 plus 0 plus 16 plus 64. These add up to 160. And I divide by n minus 1. So I have 5 values, but I'm going to divide by 4. So I get 40. 160 divided by 4 gives me 40. This is my variance. My variance is the quote average squared distance from the mean. And thus my standard deviation is the square root of the variance. So I get the square root of 40, and this gives me 6.3246. So the standard deviation of ages in the Baker family is 6.3246. If we went back, we're going to run out of time to do this, but if we went back and we did the standard deviation for the Thompson family, and so maybe, it'll probably take you 5 minutes to do this. I think it's a good exercise. Standard deviation for the Thompson, or what did I say was the other family? Johnson family? Standard deviation for the Johnson family, that is equal to 1.5811. Okay? So you can try this out. And so what we say is that the standard deviation for the Baker family is 6.3. Standard deviation for the Johnson family is around 1.6. This number is bigger than this number, therefore the Baker family has more spread in ages. Okay, we'll end there. We'll see you guys on Wednesday.